So we're going to start modeling polynomials with in real world situations. This first one where we did it as a class, and then we did 4 more problems in small groups. So make sure after you get this first one done, just on notebook or scratch paper, that you grab the problem set from Canvas or from Mr. Watisha. So this first one's dealing with football throwing. So Javon is a quarterback on a football team practicing his long throws. The height of his football above the ground when he throws it can be modeled by the quadratic function h of t equals negative 0.7 t squared plus 4.2 t plus 6, where t is the time in seconds and h is the height in feet. So first thing we're going to want to do is let's throw this into Desmos and start seeing what's going on. If you plug in this equation in the graph and go ahead and pause your screen to update it there, then we get this graph here. And you're going to see that we're probably going to need to move it around, rescale a little bit. I'll zoom out. And one thing I want to show you, and we kind of talked through this in class, is when we are using Desmos to model things, we might need to adjust some of our scales a little bit from time to time. And if you click that wrench in the top right of Desmos, you'll see you can change the size of our fonts. You can modify our grid. This step number changes the labels. So notice how I just went from every 2 ticks on the bottom to every 1 tick. So I'm going to go 1 and 1 on both my X and my Y so I can see it better. I'm going to turn these minor grid lines off just because they're a little annoying there. So now we have a nice clean view of our graph in Desmos. I'm going to go back to my slides, but you can keep your Desmos open to kind of reference the problem. So go back here, and first thing we want to do is graph the function, Desmos, boom, we've done that. And let's start by asking the questions, what is represented on the x-axis and the y-axis? And on our x-axis there, you'll notice that is going to be our time. Our x-axis is going to be our time, or that's represented by t in our equation, right? And that's the same as we normally see x in this spot in our equation. Okay, that's our deep independent variable. That's our input into the problem. Our output, which is our y, that's going to be the height of the ball. That's going to be h. So I always like to identify our inputs, outputs. Using the graph is a good way to do that, especially it puts it in a good context. If you notice, this does follow about the path we'd expect a football to go, right? It starts at about the height of the person, reaches a max point, and then decreases until it hits the ground, in this case about 7 seconds later. So let's keep moving through this. To calculate the initial height of the football when Javon throws it, we are going to plug in the time, the initial time when he would throw it. And that is going to be when time equals 0. Right? If he initially threw it, our time should equal 0. So we can plug in our formula, h of 0 equals negative 0.7 times 0 squared plus 4.2 times 0 plus 6. And in this case, that's equal to 6 feet. Right? The zeros cancel each other out as we go through the problem. You can plug it in a calculator, or you can just know that's how it goes. And if we think about it, that makes sense. On our graph here, at 0 seconds, at our y-intercept, the ball is 6 feet off the ground. That's exactly where we would expect. It's just leaving the thrower's hand. Now, if we wanted to calculate the height of the football after 5 seconds, we kind of follow a similar process. We just plug in 5 instead of 0. So t equals 5. So h of 5 equals negative 0.7 times 5 squared plus 4.2 times 5 plus 6. And we'll need to use a calculator to calculate that. So go ahead, pause your screen, try it out real quick. And we should get 9.5 feet. Now, in this problem, I'm going to pause. I'm going to go over to my Desmos real quick and just verify that with our graph. It looks a little bit different. So if I go back to my Desmos And we're trying to calculate after 5 seconds. So I go over to t equals 5, and I'm going to move my cursor up to my graph, and I'm going to click on it right about where t equals 5. And if I click and hold, notice how my dot will move, and my x variable here, my x number, the 5 out in front, that's our seconds. And that second number, the y, that's our output, that's the 9.5 feet. So geographically, we can verify that as well. And it's important, we want to be able to work through it two ways, both calculating and verifying it with our graph. So let's move on, just a couple more questions to answer. So what is the maximum height the football reaches, and what time does it reach this point? This one we are definitely going to want to solve graphically. So if I go back to my Desmos, we kind of do the same thing we did, right? We can trace, if you click and hold and kind of trace your finger up, we can reach that local maximum point. Looks like about right around 3 seconds. Or you'll see if you click on your equation, and let me make this bigger real fast. If you click on your equation, you'll notice this gray dot shows up at our local maximum. Okay, Desmos does a really good job. It locates those zeros for you exactly. It locates the y-intercept. It also locates any local points. So I'll kind of zoom out again. If I click there, it looks like, all right, at 3 seconds, our x variable, we are at a height of 12.3 feet. So we don't expect you to calculate that. That's something you'll learn how to do in calculus. But we are at a maximum height of 12.3 feet at 3 seconds. And final question, just analyzing the graph here. How long is the ball in the air? We could estimate it just by looking at it somewhere between 6 and 8, so maybe 7.5 seconds. Or we can do what we just did earlier, is go back to our graph. If we click on that graph, that gray dot shows up right at the bottom, and we'll see at a height of 0, so that second number, comma 0, it was 7.192 seconds. So that's how long the ball is in the air, and we can write that down, 7.192 seconds. So again, this is the only problem we did as a large class. Then we went into group work, and just make sure that you grab the problem set either from Mr. Ratisha or from Canvas, and that he sees the work when you are finished.